Let's specify the characteristics of the proposed case inverter and battery. Looking at the system, the first complication we see is there are actually two inverters in this system. There's the PV inverter, which exclusively converts the DC output of the photovoltaic array into AC, and then we have a bidirectional inverter here that is located between the battery and this AC bus. The cost of this PV inverter, and we'll confirm this, we'll verify this later on, is included in RETScreen's estimate of PV system cost. So if we use the RETScreen cost database to specify the price or the cost of our PV system, it will include the cost of this inverter. So we just need to include the performance characteristics in terms of the efficiency of the inverter and its size in this analysis. The second inverter, however, is 150 kilowatts AC, and it costs 2,400 kwacha per kilowatt of AC. And what we're going to do there is we're going to put that cost directly into the cost page so we don't confuse ourselves and include it as part of the PV inverter characteristics. And for the efficiency of this inverter, it's going to be lumped in with the overall energy efficiency of the battery system. So we're going to assume any losses that are occurring in this bidirectional inverter when it goes charging and then discharging the battery are specified in the battery characteristics section. We have to specify the battery. We're going to assume that it's a lithium-ion battery, a LFP battery, with 1 day of autonomy. Remember, there's fairly little seasonal variation in the load. Furthermore, the load is on both during the day and the night, so we can get away with a fairly small battery here, we hope. So pause the video, give this a try, and I will show you a solution. Alright, so we're now on step 3. We click on inverter and battery, and the first part is to specify the photovoltaic inverter. And it might make sense to wait actually for this because it's going to depend on the size of the photovoltaic array we pick, but I'm just going to put it at 150 for right now, and let's see if that makes sense. For the efficiency, I can use the help to come up with initial suggestion of 97%. I will adopt that. For miscellaneous losses, I'm going to assume none, and for the initial costs, I'm going to leave that as blank. Why? Because, as we will see later, those are included in RETScreen's cost database when we provide the cost of the PV system. So I'll leave that out. Now I'm adding the battery. And just before I fill out these, so that I don't forget, I'm actually going to go over to the cost page here and put in the cost of our inverter here. So I go to the cost page and I'm going to go to level 2 so that I can specify the size of the inverter here. And the inverter cost is now for the bidirectional inverter. And we know that's 150 kilowatts, so I can use that figure here, and I will put in a value of 2,400 kwacha. So the bidirectional inverter cost is 360,000 kwacha, and the cost of the PV inverter is going to be included in as part of the PV system. So for the battery, we want 1 day of autonomy. The voltage is not a critical parameter because ultimately it's just going to adjust how many amp hours are suggested here to generate a battery with a given kilowatt hour capacity. So I'm going to assume something in the neighborhood of 100 volts. It's not that important. For the efficiency, however, this is important. And here we're including the battery efficiency, which for a lithium-ion battery might be somewhere around 90 to 93%, and the losses in the bidirectional converter during charging and discharging. So here I'm going to say that the overall efficiency is, say, 85% of the combination of battery plus bidirectional converter. For the maximum depth of discharge, I'll assume 80%. You can find information about recommended maximum depth of discharge on the cost database. So if I click on that, for example, it shows that for lithium-ion batteries, 80 to 100% is a reasonable maximum depth of discharge. For the charge controller efficiency, I'm not going to worry about it. Why? Because I've included all my losses as in terms of the efficiency here for both discharge and charge. So I'll assume the charge controller efficiency is 100%. For temperature control method, ambient is reasonable. It leads to a very minor battery temperature derating because the temperatures are generally around 20 or 25 degrees. So I can ignore that impact and just adopt the suggested capacity here of 8,055 amp hours. Multiplying by 100 volts, that works out to an 806 kilowatt hour battery. Now we have to supply the initial costs. I'll use the cost database for that. We're right around this boundary between 10 and 1,000 or 1,000 and 50,000. So I could pick either one of these. I'm going to assume that costs are going to be a bit lower than they would be for a small battery system. So I'll pick the average costs for this larger range here. And that provides the battery costs here. So while I'm at it, I am going to take this figure here, copy it, and go back to the cost page and put that in for the battery here. Now we have the cost of the battery on this page as well. The next step will be to specify the size and characteristics of the photovoltaic array.